Okay, now that we started talking about our ideal gas relation, let's go ahead and go further with our thermodynamics review and start talking about the basic laws of thermodynamics. So why not start with number one? So first law simply says that my internal energy change is equal to my net work input plus the net heat input, and usually these are going in the opposite directions. Usually I might have work input and then heat output, or heat input and then work output, one or the other, but the difference between those two is going to lead to my change in internal energy. Now, my internal energy just depends on my final state. What pressure and temperature did I reach at the end and what was it at the beginning? That's my state. I can figure out what my internal energy was there at the beginning and at the end. As for how much heat or work it takes to do that, well, that's going to be dependent on the path, how I add that heat, how I add that work. And there's more or less efficient ways of doing that. So when we're doing problems with thermodynamics, there's a few terms that can be really helpful thinking about these relationships. First off, adiabatic. If something's adiabatic, it has no heat transfer, so there's none of this. Also, reversible. This is simply saying that I'm doing it in the most efficient way possible, no irreversibilities. I haven't lost any useful work or energy by doing it that way. And then finally, isentropic. Isentropic means there's no entropy. No entropy means I'm not losing any work, because the more entropy you have, the more chaotic your system is getting, and the less ordered energy you have that you can actually turn into work. So let's talk about that second law of thermodynamics now. First law is all about note keeping. You know the final state, you know the initial state, you can figure out the difference. Second law tells us, why does a process happen in one direction and one direction only naturally? Like, for example, if I have a hot cup of coffee, well, that cup of coffee is only ever going to get colder, okay? If it's 100 degrees Celsius to begin with, I don't know why it's boiling, but it just is. Danger. Well, it's going to get colder eventually and be somewhere around, 23 degrees Celsius. Why did it go that direction? Why didn't it just magically get hotter? That's because of second law. Second law simply says that my entropy is always going to increase. So the change in entropy for my complete system is always going to be more than or equal to 0. As a note, for an isolated system, it can be less than 0, but then it's increasing your surroundings. So in the universe, entropy is always increasing. It's always increasing. For a calorically perfect gas, where my specific heats are constant, we can get two nice equations from this. So I can say, okay, my change in entropy is either equal to this or this, just depending on what I have. So if you have specific volumes, use the second equation. If you have change in pressures, use the first equation. And for this course, we'll be using this one far more often because we typically have a change in pressure. That's how we think. And we're also always flowing, so specific constant pressure makes more sense because this is connected to enthalpy. So with that, I can find my change in entropy. But earlier I mentioned that we also have some processes where there's no change in entropy, which is isentropic. So let's figure out what those equations change into when I have that. So if it's isentropic, I set that change in entropy to 0, and I can actually develop these equations from it. This is just relating all of my values from earlier together. And so I can figure out that my ratio of pressures will be equal to my ratio of densities raised to a power, which is equal to my ratio of temperatures raised to a different power. This guy right here is our ratio of specific heat, and it's usually around 1.4 unless the problem says differently. It does change with temperature, but for most parts we're just going to say 1.4. So using the relationship, I can figure out what my change in pressure, density, or temperature would be for a reversible process. Are any processes truly, perfectly reversible, perfectly isentropic? Most of them have some sort of irreversibilities. But this gives us upper estimates, upper estimates on what we can achieve, and we can then say, okay, well, I'll never be better than that. So if I need something better than that, well, it's not going to happen. So that's it for this time. Next time we're going to be going into an example using these equations so you can see how it's used. Thanks for watching. I'll see you all in a bit. Bye-bye.